In this video, section 6.3 notes, we're going to talk about how to find the mean and standard deviation of a binomial random variable and then interpret the values in context. First, let's look at the graph from the previous example on the 5-question quiz. Let's talk about the shape, center, and spread of the distribution. First of all, the shape, you notice the shape is almost symmetric with some skewing to the right. And this is because the probability is not 0.5. We talked about in previous lessons that when you actually graph the distribution of flipping 5 coins or a coin 5 times and graphing the distribution of heads, for example, since the probability is 0.5 and that's right in the middle, you're going to have a distribution that's exactly symmetric. Well, in this case, our probability of success is actually only 0.25 and our probability of failure is 0.75. And that's what skews some of the distribution to the left, because it's so much more difficult to get 3, 4, and 5 questions correct when your probability of failure is 75%, which is why the majority of the probability is here, 0 and 1. So that's why it's almost symmetric, but it's skewed to the right a little bit. The center, we'll call it between 1 and 2. We'll actually talk about on the next page how to actually find the mean. And then range will be 0 to 5. And this makes sense because in a binomial setting, we decide how many trials before we start. In this case, n was equal to 5. Now, finding the mean and standard deviation, there are 2 formulas, one for each one. First, again, let's say n is the number of trials, and p your probability of success. So if you have those 2 parameters, you can actually use these 2 formulas for mean and standard deviation. Okay, so mean. Let's say mu x is equal to, and you find the mean by doing the number of trials multiplied by the probability of success. And that's it. Standard deviation is going to be the square root of n times p times 1 minus p. So in both equations, you only need the 2 parameters, number of trials and probability of success. If you have those 2, we can actually find the mean and standard deviation for binomial distributions. Little disclaimer, these formulas only work for binomial distributions. You can't use these for other types of distributions. So we put this on here because students will frequently try and use these for other types of distributions, even though it's not possible. These only work for binomial distributions. So before you start using these, decide if you have a binomial setting first, and then move on to actually find the mean and standard deviation. If you want to find the derivation of these 2 formulas, page 398 gives you those. Goes into detail actually how it arrives to n times p for the mean, and then the standard deviation equation as well. So we're going to work through an example on page 412, number 86. So number 86 says, engineers define reliability as the probability that an item will perform its function under specific conditions for a specific period of time. A certain model of aircraft engine is designed so that each engine has a probability of 0.999 of performing properly for an hour of flight. Our company engineers test an SRS of 350 engines of this model. Let X equal the number of engines that operate for an hour without failure. A, explain why X is a binomial random variable. Go through bins. Is it binary? Do you have just success or failure? Yes. Either the engine succeeds for an hour or it fails. So binary is good to go. Independent. Are the 2 engines failing or succeeding independent of each other? They are. If one engine fails, it does not change the probability of another engine failing. N, is the number of trials fixed before we start? Yep, 350 engines are chosen. And then S, probability of succeeding, does it change? Nope, it's the same throughout. Every single trial is the exact same success probability. So bins works out here. Running through that verbally, go through those 4 checkpoints to see if it follows through, and then if it does, go ahead and move on to the next part. B says find the mean standard deviation of X, interpret the value in context. So because it's a binomial random variable, we can use the formulas we just talked about in the previous part of the notes. Finding mean, we're going to do n times p. N is 350. Probability of success is 0.999. So we're going to do 350 times 0.999. And when you do that, you get 349.65. So a interpretation in context, you could simply say for mean, after many tests of 350 engines, the average that would succeed is 349.65. So you see that this first part here, after many tests of 350 engine, kind of follows through from previous chapters and sections about stating interpretations of mean. Let's find the standard deviation. So let's make a new part here. Sigma x is going to be the square root of 350 times 0.999 times 1 minus 0.999. And when you calculate that, you get 0.59. So interpretation of this, essentially the same sentence, except for you're going to talk about how much it differs from the mean by. So steal this part. After many tests of 350 engines, the average should differ from mean by 0.59. Something simple like that will work. All right, let's try and save some room for part C here. Part C. This says, 2 engines failed the test. Are you convinced that this model of engine is less reliable than it's supposed to be? Compute the probability of X is less than or equal to 348 and use the result to justify your answer. So what is that number? Because if that number is really large, or larger than you think it's going to be, is it less reliable than what the probability seems to be? So the probability of less than or equal to 348, we can use our calculator for that. Since this is binomial, we're going to go to second vars for distributions and go to binomial. Now there's 2 options here for binomial. There's PDF and there's CDF. You're going to want to choose the one that's cumulative, CDF, because you're doing less than or equal to a number. So you click on that one. N is the first number, 350, comma. Next is the probability of success, 0.999, comma. And then how many successes is the third number, 348. And when you do that, you get a probability of 0.049. We'll round it to. The probability ends up being 0.049, and the probability of that is pretty much close to 5%. So the probability of this happening is less than 5%. And since that probability is so small, it's likely that these engines are less reliable than they're supposed to be, at 99.9% reliable. This event happened and less than 5% chance of it is happening. We say that it's statistically significant for it to happen. So we're going to say that this is less reliable than that the company's putting out for there being.